let's take a look at some problem solving with curve sketching. So using first and second derivatives, seeing kinds of problems with that, and a graph. So this first one, we're going to look at all these criteria we have and try to build up a sketch of a graph that satisfies these criteria. And we're just going to basically go through it kind of one piece at a time. So what I always like to start with is, well, we're given asymptotes. Let's just graph x equal to -1, y equal to 0. It doesn't even matter what the rest is. We know those asymptotes will go on there. So here is x equal to -1. And a nice straight line. Y equal to 0 going across. Make sure to label as asymptotes. Okay, then we have information about increasing and decreasing, as well as the concavity. And then some information about some specific points there. Oh, and this limit here, it should be going to plus or minus infinity. So just telling us the end behavior. Okay, so let's start actually then after we've got those asymptotes down. We've got some specific points. Let's get those specific points down. So we have the point 0, 0. And we have the point 3, 5. I'm going to do that about. Let's do that about here. All right. And then I'm going to go left to right, basically trying to satisfy both the first and second derivative as we go from left to right, as well as the asymptote behavior. So we have the asymptote is going to be from above as we approach positive and negative infinity. I'm just going to add little arrows at the ends. We know that's where we have to end. So now let's go left to right. So going left to right. So we're starting at less than -1, less than -1. We're looking at both those intervals. So we know that the graph is going to be concave up and increasing by the first and the second derivative. So it's going upwards, and well, since it's concave up, it'll curve like a U, like that. Nice and smoothly. It's not the smoothest there, but it should be nice and smooth. Okay, now let's look at, well, after -1. So the next kind of interval that I can see after -1, so we're going from -1 to 0, -1 to 3. So we'll first start off with the concave down part to 0. And we're increasing on that interval. So got the asymptote there. So to increase, we have to be approaching the asymptote in that way. And we're concave down. Here, let me just label these as well. So we start off with concave up and increasing. And now we're concave down and increasing. So you can see the difference there in how it's shaped. Even though they're both increasing, the concavity does make it look different. All right, now let's go back up. So now we're looking past 0. So we're looking at, let's say, bigger than 0, but we're still in this initial range where we're less than 3. So we're going towards that point there. And as we go towards that point, what we can see is that we're increasing, and now we're concave up. So we're going to curve like we did before, basically, all the way to that point, like that. Okay, so that satisfies that. So now I'm just going to erase some of this, just make it a little more clear what's happening. So now we're looking greater than 3. So we're looking at this specifically, greater than 3. And, well, greater than 0 is greater than 3. So we want to draw something that's decreasing while it's concave up. So it's going to go down, but it's going to be concave up. So another U shape going downwards. Let's join that up nicely to the asymptote like that. And there we go. So again, let me label the rest of these. So concave up, increasing, and concave down, decreasing. And there we have it. So you'll see that this point's got that sharp edge. That's why if we go back to the criteria, you can see the first and the second derivative don't exist there. But as long as we fulfill that criteria, the increasing, the concavity, that's what we get. All right, so now let's take a look at the next example. So the next one, we have a cubic polynomial, x cubed minus 3bx squared plus 3cx plus d. And we know that has a minimum and a maximum at those 2 points. And we want to prove that the inflection point, or the point of inflection, is at the midpoint of the line segment. Okay, so let's first of all just get some derivatives done. So I'm going to do the first derivative, which will just be 3x squared minus 6bx plus 3c. Okay, we can common factor to get x squared minus 2b x plus 1, or c, I should say. And then let's also do the second derivative. And that will be 6x minus 6b. Common factor, and you get 6x minus b. Okay, so what we can see is the one and only potential inflection point we might have. So h prime prime of x equals 0 at x equal to b. Okay, that's going to be useful for later on. But let's deal with the first derivative now. So we want to find when h prime of x is equal to 0. And what that means is we've got a factor, or in this case, well, that doesn't look easy to factor. We're going to have to use our quadratic formula. So if we use our quadratic formula, negative b, which will be, well, 2b in this case, plus or minus b squared. So 2 squared is 4. 4b squared minus 4ac, which is going to be 4 times 1 times c, all over, well, the entire thing over 2 times a, which is just 2 times 1. Let's simplify this a little bit. You can take out a common factor of 4 from that square root, so I'm just going to write it out in front. And you're left with b squared minus 4c, all over 2. But the square root of 4 is just 2. And so if that's 2, all the 2's will end up canceling out. And so you're just left with b plus or minus square root of b squared minus 4c. And so let's just make this correspond to our 2 points. We have x1 and x2. So x1 is going to be, let's say, b plus the square root of b squared minus 4c. And x2 is b minus the square root of b squared minus 4c. All right, and what does the question ask? It's asking, well, basically, are those 2 critical points? These are what they are. The critical points, which are the maximum and the minimum. Well, is the point of inflection at their midpoint? So let's find midpoint of x1 and x2. And how do we find the midpoint? Well, it's just the average of the 2 points, which will just be x1 plus x2 over 2, which in this case will be b plus b squared minus 4c plus b minus now b squared minus 4c, all of that over 2. Well, the square root parts, they nicely cancel. So you're left with 2b over 2, which, well, what do you know, equals b. And therefore, the midpoint matches, well, look at that. We had said h prime prime of x is equal to b, or it has a 0 at b, and the midpoint itself between those 2 critical points before is equal to b. So therefore the midpoint of x1 and x2 is equal to the point of inflection at x equal to b. And there we have it. That's our proof. All right. And so now you're going to try some whole bunch of problem solving yourself.